Okay, welcome to video 263. Okay, energy and reactions. Let's take a look at this figure. Figure 12, modeling activation energy. The rock at the top of the hill cannot roll down the hill until a small push gets it going. Question, how does this cartoon make a kind of model for the role of activation in a chemical reaction? Okay, let's read. Energy and reactions. To understand why it can be hard to start some chemical reactions, look at figure 12. The rock at the top of the hill can fall over the cliff, releasing energy when it crashes into the rocks at the bottom. Yet it remains motionless until it's pushed over the small hump. Activation energy. Vocab word. Every chemical reaction is like that rock. A reaction won't begin until the reactants have enough energy to push them over the hump. Where's the hump? The hump is right there. Over the hump. Let's move up. Over the hump. The energy is used to break the chemical bonds of the reactants. Then, the atoms begin to form the new chemical bonds of the product. The activation energy, another vocab word, is the minimum amount of energy needed to start a chemical reaction. All chemical reactions need a certain amount of activation energy to get started, and this is absolutely true. All chemical reactions need some activation energy. This looks like a good quiz question. Consider the reaction in which hydrogen and oxygen form water. This reaction gives off a large amount of energy, but if you just mix the two gases together, they can remain unchanged for years. For the reaction to start, a tiny amount of activation energy is needed, even just an electric spark. Once a few molecules of hydrogen and oxygen react, the rest will quickly follow because the first few reactions provide activation energy for more molecules to react. Overall, the reaction releases more energy than it uses. Recall that from section 1, this type of reaction is described as exothermic. Exo means out, thermic means heat. Exothermic, heat being released. Okay, please move on with me to page 206. 206. Exothermic and endothermic reactions. Every chemical reaction needs activation energy to get it started. Whether or not a reaction needs still more energy from the environment to keep going depends if it's exothermic or endothermic. Exothermic reactions follow the pattern you can see in the first diagram in figure 13. The dotted line marks the energy of the reactants before the reaction begins. Oh, wait. Okay, so I'm just going to put a little mark where I stopped, and let's go look at figure 13. There we go, figure 13. So here is where the energy of the reactants is, where it starts. Okay, and this line represents time down here and energy here. So as time goes on, you have to give it a push, a boost of activation energy. And once it gets to the top like a roller coaster, then it falls all the way back down to the bottom. Okay. So in the end, the products have less energy than the reactants. This is exothermic. But in the opposite, if the products have more energy than the reactants, then that must mean that took some more energy, heat is absorbed to make it happen. So basically, it's endothermic. Let's keep reading. Notice that in the peak in the graph shows the activation energy. Notice that at the end of the reaction, the products have less energy than the reactants. This difference results in a release of heat. The burning of fuel, such as wood, natural gas, or oil, is an example of an exothermic reaction. People can make use of heat that is released to warm their homes and cook their food. Now, look at the graph of an endothermic reaction on the right of figure 13. Endothermic reactions also need activation energy to get started, but in addition, they need energy to keep on going. Notice that the energy of the products is higher than the energy of the reactants. This difference tells you that the reaction must absorb energy to continue. When you place baking soda in vinegar in the discovery activity in section 1, we didn't do that, but if you want to do that at home, just ask your mom for some baking soda and vinegar, they probably got it, and try it out. The thermal energy already present in the solution was enough to start the reaction. The reaction continued by drawing energy from the solution, making the solution feel colder. But most endothermic reactions require a continuous source of heat to occur. For example, baking bread requires added heat until the baking process is completed. Oh, that makes sense, I guess. And so that's why things bake if they're hot and don't bake if they don't. All right, once again, let's check out this graph for exothermic and endothermic. The key here is if the products have less energy than the reactants, it is exothermic. But if the reactants have less energy than the products, it's endothermic. This hump always means activation energy. Oh yeah, this graph looks like a great quiz question to me. All right, please go ahead and go to the next video.